Okay, so let's work on the beautiful idea of the kernel trick. So let's understand the why for the kernel trick. So let's talk about the SVM because it's one of the major uses for the kernel trick. Here you can see that I have two sets of data, one in blue and one in red. And I want to make this separate line that will separate the data to the two groups so I can separate what I get. Example, a new point so I know to which group it is used. Now, in two-dimensional space, there is no linearly separable category. There is no linear line or plane that I can use to separate the data. The separation line is, of course, non-linear, but SVM, support vector machine, for example, usually uses a linearly needs to have linearly separable data to make the boundary. So what can we do? What can we do is we can take the problem from 2D to higher dimension, for example, to 3D. And when we do that, what happens is that we will create a subspace that will be a linear plane that will separate the data to two groups. And this can be done with the SVM when there is a linear plane that separates them. So this transformation to higher dimension is important in order to use the support vector machine. Now, there is a problem, and the problem is that moving from lower dimension to higher dimension can be very expensive, computationally, very hard computationally. So the kernel trick gives me the results that I need, which is the inner product, think about the dot product, in the higher dimensional space without ever going to the higher dimensional space. I will calculate the result in the higher dimensional space in the lower dimensional space. All the calculation will be done in the lower dimensional space, but the results will be like in the higher dimensional space. So we will save computation power. This is the idea, the core idea of the kernel trick. Doing calculation in the lower dimensions, but the result, which is the inner product, the dot product, will be as if we went to the higher dimension and there we did the calculation. So this is the idea of the kernel trick. Let's see mathematically how it is done. And here it is. Let's move throughout it, and I want to show you with an example. So without a kernel, what we would need to do in order to solve an SVM boundary, which for example is this one, for example. Okay, we have here the kernel. If we didn't have that, we will need to calculate things in higher dimension in order to create or to go to a dimension where a linear plane is able to separate the data. So without the kernel trick, we will need to take the data and explicitly map it into higher dimension space using a transformation. So we take the input, the original data x, and transform it using the theta into a higher dimension. And then after we do this, and this is without kernel trick, after we do this, we need to calculate, for example, the inner product in the higher dimension. But you can see that this transformation might be extremely high dimension, even infinite dimension. Now the kernel trick come and say, let's do something smart. Let's take the lower dimension and there we will do the calculations, but the result of the calculation will be as if I did the calculations in the higher dimension. Namely, if we'll calculate the kernel on the lower dimension, you see the input vectors are on the lower dimension, the result will be as if I calculated the input vectors and did the transformation to higher dimension and get the result of the inner product that I need, the dot product. So I use the kernel function and use directly the computation of the original space and never construct the higher dimensional, the transformation for the lower um, dimensional vector. So you can see an example for a kernel where there are two vectors that I will calculate in their own dimension and then take the square, and this will give me the result of the dot product of them in higher dimension. Let's see how it works, for example. So here it is. I have two vectors. They are both two-dimensional, and if I want to map them into some higher dimensional space, for example, I can use this transformation. You can see that I take them to a 1, 2, 3, 4, 5, 6 dimensions. So a transformation of x will give me this. And then I need, in this dimension, I can find, for example, a linear separable plane. So in the higher dimension, I take these two vectors after the transformation and calculate the inner product between them, the dot product, and get the result. This is the result I need. But the problem, I don't want to calculate the higher dimensional vectors. It's expensive, too expensive. So using the kernel that I showed you, in this case, this kernel, this is an example of a kernel, I can just take those two vectors, two-dimensional vectors, and do this thing that I did, 1 plus x dot y in the lower dimensional space. And then take the square, everything in the lower dimension. What will I get? See yourself. I take this, which is this one, and take the square, everything in the lower dimension, in the two dimension, not in the fixed dimension. And what I get here, look at this. This is exactly what I get when I transform them into higher dimension and then calculated the inner product, the dot product between the transformed vectors. But this is exactly the result I got from doing this using the kernel, but in lower dimension, which is much cheaper to compute, much easier to compute. And this was an example for a kernel taking true dimension compared to transforming it into a higher dimension, in this case, a 6th dimension. Okay, so now you understand, and when I do that, I get a result for the higher dimension to use for a boundary, for example, of support vector machine. For example, for this one, you can see that the kernel is right over here. And I will never need to use a transformation into higher dimension. I will never need to transform to higher dimension, even though I need the higher dimension to get the separable plane. Because in this lower dimension, there is only nonlinear separable boundary. But I can use the SVM only to find a linear separable boundary. So I need this transformation. But it's very expensive, so I do the calculation using the kernel trick in the lower dimension, but get the result as if I did the transformation without ever really doing that. Because this is why it is called implicit calculation. Okay? So this is the idea, the beautiful idea of the kernel trick. Thank you all very much. Thank for Cloud for writing it down for me and for the animation you see right over here, this beautiful animation. If you have any comments, if there are any mistakes or corrections, please write it down. Thank you very much for watching it. It was very nice to explain this, and this is it. Thank you all very much.